I did this work with Jinan, Professor Tonelle, three partners from SAP. The presentation will be structured as follows. First of all, we'll go through the background of the main concepts that we used in this paper. Then we'll explore our approach, our empirical study, and draw some conclusion of this work. The three main topics of the background that then we implemented in our approach are retrieval augmented generation, the knowledge intense code generation, and the concept of self-consistency for large language models. The first one is RAG, Retrieval Augmented Generation. That is a very popular technology nowadays. It's very successful. It was proposed by Meta at NIPS 2020. The idea is that basically they combine the large language models that are parametric memories with information retrieval that are non-parametric memories. This idea was to increase and update the knowledge without needing of additional training on the model. And basically what it is that they combine these components in a probabilistic models that works in this way. We have retriever that provides latent documents, condition on the input, so the prompt, and the sequence-to-sequence model, that is the LLM, that conditions on these latent documents together with the input, so basically merges the initial prompt with the retrieved knowledge to generate a better output. And this is very successful also in industrial domain because it allows to use, for example, private documents without needing to train the model. And yeah, it's also very useful to face hallucinations that are a common problem in large language models. This is a high-level scheme that we will analyze. Basically, usually what you have in a large language model is a question. This is basically the prompt that is directly fed into the LLM. Here we're doing this sort of two branches. First of all, here you can imagine to have a sort of transformer that basically computes embeddings over this question. Then we have a vector database like Chroma, for example, that stores chunks of knowledge alongside with their embedding representation. We are retrieving some chunks here by similarity. So basically we retrieve the, for example, top 3 chunks with highest similarity with the question or the embeddings of the question. And then we concatenate the retrieved knowledge with the question itself to build the final prompt. Then basically this prompt is fed into the LLM, and thanks to the in-context learning capabilities of the large language model, we can directly exploit this knowledge to face hallucinations and also to deal with private data. And also in our project, we will see how we'll use it. Why we think that is relevant? Well, because the paper in which they introduced retrieval augmented generation is named something like how to face with knowledge intense NLP task. And here in our security domain, we are facing with something that we want to call knowledge intense function. Yeah, what is the point? Usually we have also in benchmarks for code generation like human eval, a lot of what we call reasoning intense function that are complex algorithms that can be solved simply reasoning about the algorithm. Maybe these functions are really similar to the one that you can find at a coding interview. And basically the idea is that sometimes, no matter how much you reason about a problem, you simply cannot solve it if you don't have some knowledge. For example, if I ask you something like where Leonardo da Vinci was born, you can reason a lot about the problem, but if you don't have the ground truth knowledge, you will never give the correct answer. In our security domain, we found a sort of counterpart of this NLP task in the coding world, because basically some of the security function cannot be really developed if you don't have an in-depth knowledge of this security task or this security domain, because simply you don't know how to face this problem. You can reason, but at the end you don't know the solution. And this is why we decided to employ RAG. Here we have 2 examples, very concrete, of one that could be a reasoning intense function. This one is directly in human eval, that is the most famous benchmark. Count up to n. In this function, you have to do this algorithm. And basically, I show that if you can reason about it some minutes, you can solve it. But something different is, for example, like that is a knowledge intense function. I want a function that takes a string representing a social security number, and it says true if the social security number is effectively an SSN or false otherwise. And here you can reason how much you want, but if you don't know how an SSN is built, you will never give the correct answer. Then the second main technology is self-consistency, but to introduce self-consistencies, we have to look at the chain of thoughts. The point of chain of thoughts that is proposed in NeoRIPS 2022 is that LLMs are limited in their reasoning capabilities, and we cannot simply scale up LLMs and solve this limitation. And one idea to overcome this limitation is chain of thoughts. Basically, we prompt the LLMs, and instead of requiring the final answer, we require a sequence of short sentences that somehow replicate the human reasoning process. So we go simply step by steps. And this increases a lot the performance of the NLP task. And chain of thoughts, named COT, is also extended at ICLR 2023 into self-consistency. Because another idea is that, yeah, we can do this reasoning step by step, but usually also a human mind allows multiple reasoning paths that leads to the correct answer. So what we do is that we prompt LLM with chain of thoughts, but we don't simply greedily search over this chain of thoughts, but we proceed with this sample and marginalized strategy, prompting different paths. And at the end, we determine the final answer by marginalization. One can see this approach as a sort of ensemble. It is partially true, but the main difference with respect to an ensemble is that we are using just one single LLM. We are not aggregating answer from different LLMs. We are just aggregating answer from different reasoning paths from the same LLM. Okay, now basically that we have these notions of the main concepts, we can go to the approach. The approach is based on 4 types of prompts. The one that is here is basically the basic prompt. That is the most naive way we can approach this problem. And basically what we did is that we constructed a prompt with 2 parts. The template is a general instruction that specifies what we want from the desired output. Here is something basically that we want, if we are generating code, a Python function. While the task is, in this case, the signature of the security function that is followed by a short comment describing its purpose. That is basically the one that the LLM should exploit to generate the function. Now, maybe it isn't so clear, but I have 2 examples. This is basically the template that we use to do code generation. That is something like the user will provide the initial part of the function, please generate a function formatted in this way, blah, blah, blah. And this is the task. In particular is the XSS detection task. That is one of the attacks that we care about. That is like the signature of the function. We give a string that is a GET request. We want a Boolean that is true if it's an effect. There is an attempt of XSS into the string, false otherwise. And basically we just merge these 2 parts. We fed to the LLM and this is the basic prompt. The first extension is the few-shot prompting. This is not exactly our contribution because a few shots were also exploited in human eval, because it's well known that providing examples in this way improves the performance. But since it is something that we can do in this domain, we want also to include this idea in our benchmark. Here, simply from the dataset, we extracted n examples that are, and then we did basically the call of the function. We put here the payload, and at the end, the ground truth label that is what we expect that the function returns. Then there is our contribution, basically, it is the RAG prompting. What we did is that we collected knowledge sources about vulnerabilities from OWASP and its type of websites, and we store them into the vector representation. Then we use the task, so this means this one. We compute the embeddings of this one, and we directly computed the similarity with respect to the documents that we stored in our vector store. And yeah, part of the novelty is that is like the first approach that use a function signature as the query to prompt to retrieve documents in embedding space. And then these retrieve chunks we directly append to the template. So the result is that basically our prompt is this template followed by the documentation retrieved that basically we give you some hint about this problem, and then still the function signature to be completed. And of course, RAG and few-shot can be combined because we can simply also append the few-shot to RAG to the task, and we have RAG few-shot. So this is basically an overview of this part of the approach. Here we have the 2 branches, the basic one, the few-shot, and the one enhanced by RAG. And you see that at the end, you just obtain a prompt. And regardless of this one, you can generate n functions in the same exactly way. Then there is the second main contribution, that is the idea of self-ranking, that we built upon self-consistency. Self-consistency cannot be directly applied since we cannot decompose our coding task into chain of thoughts, but we can still exploit the view of large language model as self-ensemble. Why? Because it's non-deterministic. So basically, asking multiple times to generate a function, we can obtain also with temperature 0 different functions. So what we do is that we generate a set of candidates using simply prompting multiple times, and then we ask the LLM to generate a synthetic data set, because we cannot directly ask which function is better. The LLM is not so good to determine, but we generate a synthetic data set, and then we use this synthetic data set to rank the functions and to keep just the top performing ones. The synthetic data set can be generated using the same task, but using a different template. This is the template that we use. That is basically the user will provide a signature of a function. You are a testing assistant, generate a data set that is able to test this function. So this is like the final approach here, where you have the branch that I showed before to generate the code, and then the same idea using few-shot, basic, or RAG to generate also a data set. And here with the data set, we can rank this function and keep only the one that LLM think that they perform better than the others. Now we can go to the empirical study. Basically, we introduced two different scenarios. The one that is called no training dataset. The no training dataset scenario is a dataset in which is not possible to train a deep learning model like the SOTA models to do XSS or SQLi detection. And it's also not possible to extract a validation set that we can use to find the optimal configuration of the LLM. What we can do is that basically we just try all the possible combination of the LLMs, like temperature, number of examples, RAG, no RAG, and we just observe the average performance to understand if our method on average improves the performance. The other one is the training dataset available. Here we have a task-specific training set for every task that we are considering. So basically, we can train a deep learning model like the SOTA ones, and we can compare our results with the state-of-the-art techniques. It's also possible to extract a validation set. That means that we can find the optimal configuration, doing a sort of fine-tuning of the parameters for the LLM, selecting the optimal configuration. The research question that we have is basically these four. The first one is RAG benefit. Basically, how helpful is RAG in generating the better security attack detectors, and how does it perform when it is combined with few-shot examples? Then we have the counterpart, that is the impact of self-ranking, basically how much we are improving using also self-ranking. And these two are evaluated in both scenarios, considering both the average case in NTD or also the best case in TDA. Then we have the comparison with state-of-the-art, that is RQ3, that is, of course, just in training dataset available scenario, basically how we are far from the state-of-the-art models. And then there is the most interesting question in the TDA scenario is the transferability, because we can have that for one task we are in TDA scenario. So we have, for example, think about XSS. We can have a dataset for XSS, but maybe we don't have the dataset for another vulnerability. So we can train just one state-of-the-art model. But what we can do with our method is that we use the TDA to get the best configuration in a dataset, in a task A, and then without the dataset, transfer blindly these parameters to another task and see how good is the result that we obtain with these parameters without using any dataset. In our empirical study, we use different models. Basically, we have all these models for code generation that are GPT models, Claude-free models, Palm, Llama, Mixtral, and you see that some of them are not in both generation and data generation because they not work so well in both tasks. So some of them are just discarded. Then we have free temperatures, 0, 0.5, and 1. A number of few-shot examples, 0, 2, 6, 10, where 2 basically means that we have 1 positive and 1 negative, 6, 3, 3, and 10, 5, 5. And then the possibility of using or not using RAG in all the other configurations. We consider 2 different tasks, XSS detection and SQL injection detection. This is the sizes of the dataset that we have. And okay, one can argue, why do you keep this large number of training examples if you just use at most 10 examples for few shot? It's true, but we did this split because we want to compare directly with trained models, like deep learning models. And for them, we should use this number of these training sites. And then considering other settings, we use 3 values of K for top K selection using self-ranking, 1, 3, and 5. To account for non-determinism and exploiting self-ranking, we generated 40 functions at every iteration and 10 synthetic data for every iteration. And the performance metrics that we used are F2 score, that is, well, it is nice in the security domain because usually we care more about recall than precision. And then general accuracy, since we are in balanced data set setup, we can also use accuracy. And these are basically the results for RQ1. We see that these are the one considered on average, and you see that almost for all the model temperature configuration, using RAG improves the performance. For SQLi is pretty good until 20%, but for XSS is even better. We can reach 40% of performance improvement for some configuration. And while considering the TDA, the training data set available scenario, we just simply analyze that the best configuration uses RAG. So also in this case, it's useful. Then we have RQ2, that is the impact of self-ranking. This is just for XSS, but also here you see that using self-ranking is much better than don't using it, because most of the times you are improving, and you're improving also a lot. If you're lucky, you can get also 60% of improvement, while if you are really not lucky, you just lose 10, maximum 20, but in very minimal cases. So it's like a good bet to use self-ranking. And we have slightly worse result with SQLi, but still most of the density is above 0. So it means that it's better to use it than to do not. Finally, we have the comparison with state-of-the-art. We are slightly worse than state-of-the-art because state-of-the-art is almost perfect, I would say, in this simple task. But what we did is that we also consider a baseline, that is basically what we can reach using just the basic prompt, so without any of the proposed technique. And we see that compared to the baseline, we are much, much better, and we almost reach state-of-the-art. And of course, we had the advantage of transferability that we'll discuss in the next slide, and also some good points regarding the interpretability, because we generate function that we can interpret, while state-of-the-art models are just black box network that they are not so easy to be interpreted. Then we have the transferability. Here we see that basically if we transfer, we lose some point of F2 score in this case. But if we compare with the average, so that basically represents selecting a random combination of all the model temperature few shot, we are much, much better. So that means that when we transfer blindly to another task, of course, it's not the optimal setup, but we are much, much better than an average case. And of course, also for SQLi, the same idea holds. We obtain results that are slightly worse, but much better than the average. And basically, yeah, that's it. We have some conclusion. What we did is that we integrated RAG and self-ranking to improve the security of LLM-generated attack detectors. We studied the effects of 9 LLMs targeting 2 attacks that are SQLi XSS. We demonstrated that the approach is effective with a notable performance improvement. And yeah, the results show how important it is to incorporating relevant knowledge and to develop automated assessment method for LLM-generated code in the domain of security, and probably also in other domain of LLM-generated code. The next step of our work is that we can consider to customize the RAG retriever to be better suited to merge documentation embeddings with code embeddings. Then we want to explore other software engineering scenario in which using RAG is potentially beneficial. And also it's interesting to consider the relevant information as a possible vector of attack, because another attack that we are considering is data poisoning, and we want to exploit also the usage of RAG as a way to use data poisoning without training the model. And finally, I want to consider other security aspects of code generation, such as poisoning. I will conclude the slide with a summary of the approach, and thank you for your attention.